Hello everybody, this is the first video associated with chapter 5 of the course. The purpose of this chapter is to illustrate a set of methods called Monte Carlo methods to learn either the optimal policy of a Markov decision problem or the associated value function. In the previous chapter, we introduced dynamic programming frameworks and we saw drawbacks associated with these methods. So now in this chapter, we'll introduce genuine reinforcement learning approaches. Okay, so the approach used in Monte Carlo methods does not require to have a prior knowledge of how the environment works. So recall in chapter 4 where we used dynamic programming, we had to assume that we knew what the function P, the transition function between the various states, we had to assume we knew what it was. Well, in practice, in many problems, we don't. So these Monte Carlo methods, they work in a context where you don't necessarily have prior knowledge about the dynamics of the environment in which you optimize the behavior of your agent. Okay, so this chapter covers chapter 5 from the textbook. So we saw a framework in the previous chapter where instead of calculating directly the optimal value function in policy, we had a framework where we started with any policy or in any estimate of the value function, and we typically refined them progressively through a scheme which was called generalized policy iteration. Okay, so you start with some policy, you refine your estimate so that your value function looks more like the one associated with your current policy, and then from this new value function estimate you build up a new policy with the policy improvement approach we discussed in the previous chapter. And as we mentioned earlier, all these steps, so policy improvement and policy evaluation, both required transition probabilities P, which for some problems, as mentioned, don't exist. And okay, so this is one issue. Sometimes we don't know P, but there's also other issues we haven't discussed yet. So let's say we have a fixed policy, for instance, and let's assume we want to do some policy evaluation, which is we want to estimate the value function. Then the framework we saw in the previous chapter involved designing a sequence of value functions which converge to the true value function associated with a given policy. And to obtain this sequence of value functions, we had to go through the following scheme here. Okay, so we had that for a state S, the next estimate of the value function involved summing across all possible next states and all possible actions of the next reward plus the discount factor times the value function estimate at the next state, and these values are of course weighted according to their probabilities. Okay, so this can be interpreted, maybe I'll write it here, this can be interpreted as the expected value of the next reward plus gamma times our current estimate of the value function at the next state. So here VK means current estimate of the value function given ST is equal to S. Okay, so this is the interpretation of the formula below. Whoops, and given, AT is equal to A also. Okay, because we assume it's for a fixed policy, so the action A is fixed. Okay, and here, okay, so that part, the reason why we had that, maybe I'll erase this. Here it's implicit that we take action A because in the last chapter we said we consider deterministic policies. So in a given state, there's a single possible action. Okay, so this condition where AT is equal to A was implicit if you consider deterministic policies. Okay, so this was the policy evaluation scheme. We had to refine the value function. And then first thing we said is that if we have to do that for all states S, so here this is for a single state S, but if we want the function vk plus 1 for all states, we have to do a sweep across all states, which is to do that for all states S, and this would most likely take too much time for very large problems. So a solution we had is to do that for a subset of states. So instead of doing for all states, we could instead have done for some states. Some states. Okay. So in the limiting case, we did the policy evaluation with only one single state at a time. Okay, so this was known as asynchronous dynamic programming. Okay, this seems nice. This seems to be shorter, and it is shorter, but is it sufficiently short? Because even if we do that policy evaluation update for a single state S, we still have to sum across all possible states S prime and all possible rewards. Okay, so let's say let's forget about this summation for the reward. Let's only consider the first summation. So if there are 10 to the 20 states or something like that, like in backgammon, summing this expression across all the states is impossible. Okay, so even if we do asynchronous dynamic programming, sometimes the sum for a single state S, so we have to sum through all next states. Sometimes this summation is way too large to be applicable in practice. So again, for that reason also, dynamic programming might fail. So methods we will introduce in this chapter, they aim to be applicable in these types of situations. Okay, so we aim to be able to apply them even if the number of states is large and the number of possible rewards is also large. Okay, so the previous drawbacks associated with dynamic programming algorithms, they call for the development of new methods. Okay, so these new methods that we would need, they need first to rely purely on experience. Okay, so if the update function for the value function or the algorithm in general we use relies on knowing P, the transition function, then we must have a problem. So our algorithm must be applicable without prior knowledge on that function P, the transition function. And furthermore, for many problems, we cannot have summations across all possible states. Okay, so to be applicable, for many problems, we cannot consider all possible transitions from the current state action pair to the next reward and next state, because sometimes the number of such possible transitions is very large if there are many states and thus many possible values for S prime. Okay. A quick note here, the methods we're going to introduce, we said they work in a context where P is unknown, but still, even for problems where P is known, they can still be useful. Okay? Why is that the case? It's because sometimes we're going to see that it's much easier to simulate outcomes from the from the Markov decision process than from calculating transition probabilities. Okay, so there are many games where you could, in theory, calculate transition probabilities, but these would involve pretty complicated combinatorial calculations, so it might be simpler in that case not to compute them at all and use the reinforcement learning algorithm. Okay. So the key idea that is used by the Monte Carlo algorithms of reinforcement learning, which we will introduce in this chapter, is the following. The key idea is to use Monte Carlo simulation of the Markov decision process to generate random returns. What's a return again? A return is the sum of discounted rewards. So you can simulate the Markov decision process, state, action, reward, state, action, reward, state, action, reward, etc. Calculate the returns at all the various steps. And then you can approximate the value function of a state as the sample average across all simulated values of your return when you are in state S. So this is the key idea on which we're going to rely next. Okay, we're going to discuss some more details these algorithms, but this is the idea we're going to use. A quick note, in this chapter, we're going to assume that, or we're going to consider episodic tasks. Okay, so we're going to assume that each Markov decision process must end at some point. There's a terminal state, and at that point, the episode stops. The reason for that is that in episodic tasks, all the episodes terminate, and therefore, you do have the return that can be calculated. Okay, because otherwise, for continuing tasks, where you have an infinite number of time steps, then you can never calculate the return because you have to sum across an infinite number of time steps. Okay, recall that the return is the sum of all future discounted rewards. So in theory, you cannot simulate an infinite number of random rewards and sum them all. So we will only consider episodic tasks. In practice, though, we can often approximate a continuing task by episodic task. Yeah, I'm gonna write why I haven't written that in the slides, but it's good for you to know. It's because the return here at some time t, we defined it as the sum. J goes from 1 to infinity of our t plus j gamma to the power j minus 1. Okay, but the idea here is that if the discount factor is smaller than 1, then eventually, when j is super large, all these terms will be very, very, very small and negligible. Okay, so here, even in continuing tasks, often you can approximate the return by having a finite sum instead. So you could have 2d, where d would be a finite integer of here, the same thing. Here, this is the same thing. Okay, so because for continuing tasks, you can approximate infinite sum by a finite one, you could also approximate returns. So these methods could be somewhat applicable in practice. Okay, they would be an approximation, but if d is very, very large, then it becomes a very decent approximation. Okay. Okay, so again, how does it work? In Monte Carlo methods, you simulate. So right now, let's consider a fixed policy. Okay, eventually we'll go to optimizing the policy, but for now, let's consider some fixed policy. So the idea would be to estimate, again, simulate many paths of the Markov decision process, and then the idea would be that you could approximate the value of a state action pair as the average return. And when I say average, it's average across all the paths and all the steps you've simulated when I'll average, let's call it GT, whenever ST is equal to S, AT is equal to A. Okay, so this means that you simulate many paths of the Markov decision process. You check all the stages and all the paths for which at some time t you're in the current state S, and you take the current action A, and then you can approximate the value function at that state action pair of the average of the return across all these stages and paths. So you can draw parallels of what we're doing here with the multi-armed bandit problem we considered in chapter 2. Okay, so in chapter 2, again, we estimated, well, for many algorithms, we've estimated the expected reward of a given arm by averaging all the rewards we had from that arm. Okay, so in the chapter 2, this is how we proceeded, and then we discuss at the end a generalization where you have different states. So maybe your slot machine has blue and orange as an indicator, and every time you have a blue color, you have one set of distributions for the arm. Every time you have orange, you have another set. So then the value of the various arms is different across the states. Okay, so again, this is analogous to the situation. So you can be in many possible states, and for each of these states, the value of the various actions is different. However, what's the difference between the fully general Markov decision process framework versus the bandit problem? It's because now the plays, which we call the stage in this chapter, they exhibit some form of interdependence. Okay, so every time you sample or you choose an action, you end up transitioning into a state, and the action you're taking has an impact on the next state. Okay, whereas in the contextual bandit, this didn't happen. Okay, so let's say you had a blue color at one point, then you take an action, and then at the next step, the color wasn't influenced by your previous action. Okay, but here in the Markov decision problem or process, every time you sample from an action, this influences the subsequent state. So in that sense, the reward you get from the various time points is interdependent in that Markov decision process, whereas it wasn't in the bandit's case. Another difference, okay, between the current framework and the bandit's problem is that in the current framework, so we said earlier we consider a fixed policy, but now let's consider the case of the generalized policy iteration, where we have to progressively refine our estimate of the optimal policy. So as you refine your policy, you continue generating new paths, and because your policy is changing across time, the distribution of your paths, meaning the rewards, actions, and states faced in the various paths, is changing. So now this becomes some form of non-stationary problem, because the distribution of your rewards and states changes through time as you go by. So you're not in the IID case. IID stands for independent and identically distributed case when you learn the policy. So when there's policy learning at the same time then you generate paths, then you have your distribution of rewards and therefore the value function, the value of the various states changing through time. Okay, so this is another difference between the Monte Carlo approaches we study in this chapter in comparison to the multi-armed bandit from the previous chapter. Well, from chapter 2, in fact. Okay. So we're gonna see that the methods presented in this chapter, they have parallels to what we saw in chapter 4 when we discussed the generalized policy iteration approach. Okay, so exactly like in chapter 4, we do start with an initial policy, an initial value function, and then we're going to refine through time their estimates, and their estimates interact together the same way than they did in chapter 4. So when we refine our estimate of the optimal value function, we can use that new estimate to define a new policy which should be greater in theory, and then that new policy can help determining or updating our estimate of the value function. Okay, so the main difference between what we do in this chapter and the previous dynamic programming chapter is instead values of the various states in action are learned from experience instead of being computed through the Bellman equation. Okay, so in reinforcement learning, instead of calculating all the possibilities and come up determining the value of the states through calculations, we will instead learn them by experience. And this is analogous to how humans learn in practice. Okay, so when you learn how to walk, you don't try to calculate what would be the various possibilities of the various movements and then end up with, okay, well, this is the best way I should walk. No, you just try walking, see what works, and eventually you end up improving on your policy, so being able to walk. So in some sense, it's a very natural way to learn problems, and perhaps this is why it works well in practice. Okay, so the first algorithms we're going to propose involve only learning the value function for a fixed policy. Okay, so we're going to fix by the policy. Again, what's a policy? It's the mapping which takes a state and an action and return its associated probability. So it tells the probability of taking the various actions in a given state. So we're going to fix that policy pi, and we're going to do the policy evaluation problem where we try to find the value function for that fixed policy pi. Refining the policy and learning the policy will come subsequently in the chapter. Okay, so recall that for a fixed policy pi, okay, the value of a state, Vs, V pi s in fact, is the expected return, so the expected value of all the sum of future discounted rewards when we start from that state. Okay, so in here it means that V pi s is equal to the expected value of GT given we start in state S. Expected return given we start in S. Okay, and here this we can maybe denote it E pi here, or put the pi on the as an underscore here. This is to denote we follow policy pi. So as we said, what we can do, we can simulate many paths and try to find at which point we we fall in that state, and then we're going to average all the returns associated with all time points and paths in which we were in that state. Okay, so and through the law of large numbers, this average of returns should converge to their true mean, and the true mean is the value function of that state. Okay, so this is the strategy we're going to use. Okay. Okay, so again, this is recalling what we said. So suppose we want to estimate v pi s for a given state s. This is the expected return starting in state s. So we assume that we have a list of episodes that we've generated, all with the same policy pi, where the state here was visited in all of these episodes. Okay, so if ever you simulate many episodes, all the episodes where you never visit S, well, they won't be helpful for calculation, so you can forget about them, and then focus on all episodes where S was encountered. So every time you visit S in these episodes, or the state S occurs, this is called a visit to S. So a visit to S is the time point for a given path where your current state is S. So for a given path, there might be multiple visits to S. So for example, if your state's sequence is 1, 2, 3, 1, 3, then state 1 and state 3 were visited twice. So in that case, you have a path with multiple visits to state 1 and multiple visits to state S. Okay, so when there are multiple visits to a state S, we refer to as the first visit as being the first time S is encountered in a given generated path. So there are two distinct Monte Carlo approaches. The first one is the first visit methods, first visit Monte Carlo method. This method estimates the value function v pi s as the average across all episodes of the return following the first visit to S. Okay, so let's say I'll give an example. So let's say we have a path where the sequence of states is 1, 2, 3, 1, 3. And let's say, let's say we only generate one path. This is a simple example. Okay, so let's say we only generated one path. So this is a sequence of states. This is the sequence of, well, let's call it gains. Okay, so let's say this is 5, 4, 3, 2, 1. Okay, so you have a return of one, reward of 1 every time step in that path. Okay, so here in the first visit MC method, the estimate of the state 1 here would be v pi s, v pi 1 would be approximated by the average of all returns, where but only for the first time you've encountered state 1. Okay, so here here in this path, you faced or encountered state 1 twice, but the first visit only entails taking the return associated with the first time you faced state S. Okay, so this is called, this is the first visit method. And there's the every visit method. So the every visit method, instead of averaging only across the first visits to state 1, you average across all visits to state 1. So your estimate would be, in that case, first visit, your return is equal to 5. Second visit to 1, your return is equal to 2. So here divided by 2, which is 7 halves, okay, or 3.5. Okay, so in the first visit method, you estimate the value of the state as the average across all paths of the return in the first visit to state S, whereas in the every visit method, you average not only returns in the first visit, but returns in all visits to S. Okay. So are these approaches sound? So do they give good estimates? A first thing we can say about these is that if there's a number of paths simulated, then both estimates, the first visit Monte Carlo estimate and the every visit Monte Carlo estimate, they both converge to the true value function. Okay, so as the number of visits or the number of paths goes to infinity, number of visits to state S. Okay, so in the first visit Monte Carlo approach, it's easy to see why this is the case. Okay, because every time you have a visit to S, it must be in every time you have a first visit to S, it must be in different paths because we only account for the first visit in a given path. So because of that, at every first visit across the paths, the returns you obtain are independent because all the paths are generated in an independent fashion. So for this reason, the returns associated with each first visit to S, they are identically distributed, but also independent because the various paths are simulated independently. So it's a very well-known result that when you average IID random variables, their average will converge to the mean with probability 1. Okay, so this is the strong law of large number, and we know also the speed of convergence. So the standard error of the estimate, which is the standard deviation of our estimator, here it converges at the rate of 1 divided by square root of n, where n is the number of returns that are average. Okay, so as n goes to infinity, the standard error will shrink progressively proportionally, well, at least asymptotically proportionally to 1 over square root of n. Okay, so for the first visit case, it's very clear that our estimate of the state by averaging all returns associated with first visits to that state converges to the true value. For the every visit Monte Carlo estimate, proving that is not as easy because the returns are not independent. Okay, there might be multiple visits to some given state S in a given path. So because of that, the returns for this path to both visits are dependent. Okay, so for example, let's go back to our example where you had state being 1, 2, 3, 1, 2, and then the gains here, or return was 5, 4, 3, 2, 1. Okay, because we assume you have a reward of 1 in all steps. Okay, you were lucky and you got 1 every time. Okay, so here clearly the return in that at that point and the return at that point, they're dependent because both the return here and return here, they involve summing the reward at time 5. Okay, so if you change the reward at time 5, which was 1, the return here and here would both change. So you can see that the returns are dependent. The returns for all visits to state S in that path were dependent. Okay, so in that case, the return as an estimate of the mean is unbiased, but when you calculate your estimate, which involves averaging the returns, you have an average of variables that are not independent. Okay, so you do have some dependence in that case between the returns which you average. Okay, nevertheless, we can invoke weaker versions of the law of large numbers. So again, we won't go into technical details about these more complex probabilistic results, but we will just limit ourselves to saying that there are more general versions of that theorem which can still consider dependent variables where the dependence is not too strong, and you still have convergence to the asymptotically to the true average. Okay, so it can be shown that the every visit Monte Carlo estimate of the value of a state converges to the true value of that state when the number of paths and number of when the number of episodes tends to infinity. Okay, sorry. So sometimes I say paths, but I might maybe I should say episodes. Okay, well, I used these two words interchangeably previously. Okay. So one thing here that we can notice is that the Monte Carlo estimate of the value of a state, it's obtained by averaging returns. So this estimate, it's written here, does not build on estimates of other states' value. Okay, so the only input you use to estimate your value function for a state is experience. It's generated episodes. Okay, you don't use estimates of the value of other states to build on your estimate of the value of some state S. Okay, so we will see subsequently that this can be either an advantage or a disadvantage. Okay, so we'll discuss that, but this is a key difference with what we had in dynamic programming. So for example, in the policy evaluation, let's go back to this formula here. We've considered earlier. Here, the estimated value of the state S is obtained by summing across all next states and rewards the transition probability times the reward plus the discount factor times the estimated value of the next state. Okay, so in the policy evaluation approach from dynamic programming, to form an estimate of the value of a state, you had to rely on your current or your previous estimate of the value of all other states. Okay, so you had to have an estimated value, and then you refine this estimated value progressively. Conversely, for Monte Carlo approaches, we saw we don't rely on no estimates of the value function to form our new estimates of states. We just take experience as input, and we average returns across all episodes, which is the experience we've simulated. Okay. So one nice feature about these types of approach is that the computational burden associated with estimating the value of a given state S, it does not depend on the number of states. Okay, so let's go back here one slide. This was the dynamic programming algorithm we had to estimate the value of a state. So this involved summing across all subsequent states S. Okay, so if the possible next states, number of possible next states is very large, this summation would become very large. Okay, so conversely, for Monte Carlo algorithms, when possible transition between states increase and increase, it doesn't matter because you can still generate experience. You don't have to experience all possible transitions. You have only to face state S at least a few times, and then from this experience, you can learn from it, but you don't have to. So when the number of states is large, you don't have to compute larger summations. You can still take the same exact average of returns across path. So the algorithm you use won't be longer in that sense. Okay, so this is not entirely true because when you have many states, if you want to face all of them, probably you'd have to simulate more paths. But let's ignore that for now. Okay, so the complexity of the algorithm presented here, it doesn't depend on the possible number of the next states. So for a given state, it doesn't matter how many next states there are. You just have to take your fixed number of simulated episodes and average rewards across them. Okay, and as we mentioned earlier, another advantage of this approach, Monte Carlo algorithms, is when sometimes, as we said, transition probabilities are very hard to calculate, but rewards or the episodes can be very simply generated. Okay, so an example you might consider, this is in one of the assignments, but it's assumed that you play blackjack. So sometimes for example, if you play blackjack and you have a number of cards on the table, computing the probability that you get a specific combination, or let's say poker, for example. Okay, maybe let's leave blackjack aside, but poker, calculating for a given set of cards on the table, calculating the probability that you'll get a flush or like a double on the next hand, it might require a complex combinatorial calculation. Especially, for example, if you have an infinite number of cards in theory, then this might be more easy. But if you have a finite number of cards, this can become harder to calculate. Okay, so simulating blackjack episodes or poker episodes, it's much easier in practice than calculating transition probabilities. So it's much easier in that case to use Monte Carlo simulation, where you can simulate easily episodes and learn from them. And by learning means averaging rewards you obtain from given states, than computing transition probabilities and applying the dynamic programming schemes of the previous chapter. Okay, so we're going to stop here for now. We've discussed value estimates previously. In the next class, we'll expand on this, so we'll start discussing action value estimates. Okay, so let's stop there. Have a nice day.